Welcome to PSMP Pro Notes, where we simplify community medicine for easy learning. Whether you're just starting or need a quick refresher, we've got you covered with clear and engaging content. Let's get started. Hit subscribe and the bell icon for more content and check the description for notes. Welcome. In today's session, we'll explore experimental study designs, also known as interventional study designs. These are essential for understanding how interventions impact outcomes. Experimental designs are used to test hypotheses in controlled settings, where researchers manipulate one variable to observe its effect on another. Today, we'll break down the different types of experimental designs, including non-randomized trials and randomized controlled trials, RCTs, as well as their advantages and limitations. What are experimental study designs? Experimental study designs, often referred to as interventional study designs, involve actively manipulating one variable to observe its effect on another. These designs are commonly used to test new treatments, interventions, or policies. The two primary categories of experimental studies are non-randomized trials and randomized trials, with randomized controlled trials, RCTs, being the gold standard. Non-randomized trials. Let's first take a look at non-randomized trials. These trials are often used when randomization is not possible or ethical. There are several types of non-randomized trials. Pretest post-test study design, PPSD. This design involves testing participants before and after an intervention without a control group. For example, we might have 100 individuals with elevated fasting blood sugar levels. We test their fasting blood sugar levels at the start, pre-test. Then administer an intervention, such as medication or lifestyle changes, and retest their levels after a month, post-test. The study shows a before and after comparison within the same group of participants, which helps measure the effectiveness of the intervention. Uncontrolled trials. In some studies, there's no control group for comparison. For instance, the Pap smear intervention in public health systems has significantly reduced mortality due to cervical cancer. The major drawback here is the lack of a comparison group, which makes it hard to attribute outcomes solely to the intervention. Natural experiments. These are situations where natural events, like a calamity or disaster, serve as interventions. For example, after a natural disaster, like a flood or earthquake, we might observe the health impacts on the affected population, such as changes in death rates or disease prevalence. Here, the calamity becomes an accidental intervention, allowing researchers to study its effects. Randomized controlled trials, RCTs. Now let's move on to randomized controlled trials, RCTs, the most robust form of experimental design. RCTs involve randomly assigning participants to either the experimental group, the group receiving the intervention, or the control group, the group receiving a placebo or standard treatment. Steps in randomized controlled trials. Selecting suitable population. Researchers first select the target population, ensuring they are appropriate for the study. For example, if testing a new drug for hypertension, the target population would be individuals with high blood pressure. Selecting suitable sample. A suitable sample is selected from the target population. Eligibility criteria are used to ensure that only individuals who meet the study requirements are included. Exclusion criteria are applied to remove individuals who should not be part of the study. Randomization. This is a key feature of RCTs. Randomization means participants are randomly assigned to either the experimental or control group. This helps eliminate selection bias, ensuring that any observed differences between groups are due to the intervention and not other factors. Steps involved in conducting an RCT. Defining the protocol. The first step is to clearly define the study objectives. What exactly are we testing, and what outcomes do we expect? This helps set the inclusion and exclusion criteria, such as which participants are eligible for the study and which are not. Selecting the reference and experimental populations. The reference population is where you select participants who meet the study's criteria, ensuring that the findings can be generalized to a broader group. The experimental population is the group of participants who will receive the intervention. Ideally, this group is randomly chosen from the reference population to avoid bias. Randomization. Randomization is one of the most critical steps in RCTs. It is the process of randomly assigning participants to either the experimental or control group. This procedure ensures that both groups are comparable at the start of the study, controlling for confounding variables that could affect the outcomes. Manipulation. Once the groups are randomized, the experimental group receives the intervention or treatment being tested. The control group, on the other hand, receives either a placebo or standard treatment. The manipulation helps isolate the effect of the intervention on the outcome. Follow-up. Follow-up involves monitoring both groups over a defined period, assessing the impact of the intervention. This is done at set intervals to track changes in health, disease progression, or other relevant outcomes. Assessment. After the follow-up period, we assess the outcomes to determine the efficacy of the intervention. The primary focus here is to measure changes in health status, such as improvement in a disease or reduction in symptoms. Advantages of RCTs. Minimizes bias. One of the most significant advantages of RCTs is that randomization minimizes selection bias, ensuring that the experimental and control groups are comparable. This makes the results more reliable and valid. High internal validity. RCTs offer high internal validity, meaning that we can be confident that the differences between the groups are caused by the intervention, rather than by external factors. Causal inference. Since RCTs are designed to test causal relationships, they allow us to make direct causal inferences. This means we can say with more certainty whether the intervention actually caused the observed outcome. Blinding. Blinding, whether single or double, reduces both participant and observer bias. In a double-blind study, neither the participants nor the researchers know who is in the experimental group and who is in the control group, which helps maintain objectivity in data collection and analysis. Standardized procedures. RCTs follow standardized protocols for the intervention and outcome assessment. This ensures that the study is conducted consistently, reducing variability and improving the reliability of results. Regulatory acceptance. RCTs are often considered the gold standard in clinical research, especially when evaluating new drugs or vaccines. Regulatory bodies like the FDA require RCTs to establish the safety and efficacy of medical interventions. Disadvantages of RCTs: high cost and resource intensive. RCTs can be expensive due to the need for large sample sizes, infrastructure, and long follow-up periods. The complexity of these studies often requires significant funding and resources. Time-consuming. Designing, implementing, and completing an RCT can take years, especially when studying long-term outcomes. RCTs may raise ethical concerns, especially when withholding potentially beneficial treatments from the control group. Exposing participants to harmful treatments or procedures also raises serious ethical issues. Generalizability, external validity. While RCTs have high internal validity, their external validity, or generalizability, may be limited. The controlled environment of an RCT may not reflect real-world conditions, limiting the applicability of the findings to diverse populations. Loss to follow-up. One of the challenges in RCTs is the risk of participant dropout. Loss to follow-up can introduce bias and affect the validity of the study results. For example, if participants who experience adverse effects drop out more frequently, the results may no longer be representative. Complex logistics. Maintaining randomization, blinding, and protocol adherence can be complex, particularly in large-scale or multi-center trials. Managing these logistics becomes challenging and requires a high level of coordination. Not suitable for all interventions. Some interventions, especially public health measures, like sanitation policies, cannot be randomized for ethical or practical reasons. This limits the applicability of RCTs for certain types of studies. Comparison with observational studies. When comparing RCTs to observational studies, there are key differences. Control of confounding. RCTs control for confounding by randomization, whereas observational studies often require statistical adjustments to account for confounders. Cost. RCTs are more expensive, while observational studies are generally cheaper and easier to implement. Ethical issues. Ethical concerns are more common in observational studies, as participants are not randomly assigned to interventions. Generalizability. Observational studies are often more generalizable to real-world settings, while RCTs may have limited generalizability due to their controlled environments. Complex logistics. Maintaining randomization, blinding, and protocol adherence can be complex, particularly in large-scale or multi-center trials. Managing these logistics becomes challenging and requires a high level of coordination. Not suitable for all interventions. Some interventions, especially public health measures, like sanitation policies, cannot be randomized for ethical or practical reasons. This limits the applicability of RCTs for certain types of studies.